Good morning, everybody. Let's get started on taking a look at simplifying radical expressions. So we need to just go back over things that you knew from past years, but then also move it along and show you a few little tricks. Now, if you remember that if you have two radicals and they have the same index, it's as simple as just kind of scooping them up underneath the same radical. As long as n is a natural number and a and b are both real numbers, that will pretty much work. You do have to be careful if there are some negatives in there and you've got even roots, but for the most part this will work, and we're just going to go with that for our simplifying rule. Okay, so what that means that if we're trying to combine these, you can very easily just take that and make it the square root of 35, and this one make it the square root of 38. This one make it the square root of 11p, and this one make it the square root of 77x, y, z. Okay, so once again, as long as square root and square root, that will work. Square root and square root, that works. This p, there would be a little disclaimer that p would have to be greater than or equal to 0. And then that could work. And in this one, once again, x, y, and z would be greater than or equal to 0. But if you're just simplifying, you can just go ahead and do that. All right, so these having the same index, you could take the cube root of 3 times the cube root of 12 and put that together to give you the cube root of 36. Don't get fooled, this is not a square root, so the answer is not 6. It's what number times itself 3 times, so be careful you're paying attention to your index. Okay, this one would be 24 yr to the second. Okay, once again, is the fourth root, so there's no groups of 4, so we're good. Sixth root of 50 m to the fifth. And then we look at this one. These indexes do not match. So for now, the beginning of the lesson will say that they can't be simplified because of the non-matching index now. We will keep that in the back of our mind because by the end of the lesson, we will have a way of simplifying it. But for now, we're just making the point that you can't just simply scoop it up under the same radical. All right, the quotient rule tells us that if you have a certain root, you can break it up into numerator and denominator. As long as b isn't 0, which makes sense, you can't have a 0 in the denominator. A and b are real, and n is a natural number, so we're not talking negative here. Okay, so let's take a look at some examples and go over them. So this would mean that you could just simply take the square root of 16 and square root of 25 and make your work easier. This one, you would take cube root of -8, which would give you -3, or -2, sorry. Cube root of -8, which is -2. And the cube root of 125, which is 5. And simplify it by numerator and denominator. This numerator will simplify to cube root of 7. Nothing you can do with that. But the denominator, the cube root of 216, because 6 times 6 times 6 gives you 216, would be 6. Square root of 7 over square root of 36. The denominator simplifies, but the numerator does not. Because right now we're just looking for the ones that come out to be nice whole numbers without so much trouble. Okay, let's take a look and move this along with some other examples. Okay, numerator and denominator once again. And you simplify. Now you of course are stopping and pausing whenever you need to. Now we have a special thing happening here. This negative stays out here negative. And we have cube root of m to the 6th and cube root of 125. Okay, so here's the thing. Here's our little trick, is you can take the exponent divided by the index in order to simplify. Okay, because really what we're looking at here is we're looking at two groups of 3m's okay, or 3 groups of 2m's, however you want to look at that. So that gives you m squared as far as what comes out of there. So m squared, because you're looking for groups of 3, and there are 2 groups of 3 there, because m squared times m squared times m squared gives you m to the 6th. This is just a little shortcut that somebody had noticed for that, but we will talk about that. That's an important shortcut where you can take exponent divided by index. This one's just 5 because 5 times 5 times 5 is 125. Now you might want to know, how do we know that if something, a radical, is completely simplified? Okay, so we've got some rules here. You could jot them down for you to have so that at the end you're thinking about this. I've got them written here so you have something to check for, but you're going to get used to how they look. Okay, so the radicand is the number under the radical. So no exponent under the radical has to be, it always has to be smaller at the end than the index. If it's greater than or equal to, you have more simplifying to do. No radicand is a fraction. So by the time it's simplified, you have made it so that you don't have a fraction under a radical. No denominator has a radical. Rationalizing a denominator is a whole other concept, but when you're fully simplified, there's no denominators that have radicals. And also the exponents in the radicand, the number that's underneath, and the index don't have any common factors other than 1. So example, well, actually rule number 1 would cover rule number 4 as well. So let's take a look at some things and work on some simplifying techniques. We can, and for those of you who've had me before, you know that I love doing these by factor trees. Okay, because when you factor, if you're looking for a square root, you're looking for groups of 2 common factors. If you have a cube root, you're looking for groups of 3 common factors. And here you're looking for groups of 4. So if I factor 24, okay, we bring that down, you factor, so that you've got all of the prime numbers, so prime factors. I have one group of 2's here. So that means this is a 4. So the square root of 4 is 2. So that brings one number out, because here's my grouping. This is the way this looks. Every time you have a pair, you bring one out. The ones that do not have an exact match have to stay under. So my answer is 2 square root of 6 here. If you've never seen this, this is just a definite way where you have a definite end to the process. And as long as you have prime factored, then you are going to very quickly come to the end of the problem. There's another method where you're looking for perfect squares, but sometimes we can miss them. So I've got this one that's a little bit more foolproof. So we factor 108, comes down to be 4 times 27. And the great thing about prime factoring, if you didn't notice that, you would still be able to do 2 times 54, and you'll still have all the prime factors once you finish factoring it down. Okay, so we have 2, 2, 3, 3, 3. What that means, we have a pair of 2's, we have a pair of 3's. Both of them come out. And the 1 3 is left all by itself in there, so you get 6 square root of 3. 16 factors into 2 times 2 times 2 times 2. Take as much time as you need on these concepts. Then you're looking, since there are 4 of them, you're looking for groups of 3 because the index is 3. So for every group of 3, 1 comes out. It's almost like a game. 162 factors into 2 times 81, which factors into 3 times 3 times 3 times 3 times 2. So when you have that, because our index is 4, we're looking for groups of 4 of that same number. So this gives me 1 3 that comes out and the 2 that's left over underneath The negative comes just because there's a negative out in front. Okay, so the factor tree method, super nice way, and it gives you a good way of thinking about what you're looking for also when you simplify. Because we need to be able to handle these things with variables as well. So we can very easily here factor 20 into 2 times 5. And we can write out those x's, 1, 2, 3, 4, 5 of them. And when you look for pairs, we have a pair of 2's, a pair of x's, another pair of x's. The 5 and the x are left over, which gives you 2x squared, square root of 5x. Now, with the variables to a power, that's kind of a long way of going about it, but I'm showing you this just to reiterate why the next thing we do works, because it's much more efficient. Okay, handle the number the way that we just handled it, 2 times 2 times 5. Okay, so we have the 2 that comes out, and we have the 5 left over under, but the x to the 5th, if you take the exponent and divide it by the index, the number of whole times it goes in is going to tell you how many of that variable come out. So 2 will come out, and your remainder tells you how many remain or how many stay under the radical. So a 2 comes out because there's a pair of 2's, and x squared comes out because when we divide 5 divided by 2, 2 is our whole number that comes out, and you're left with 1x underneath the radical. You're always taking exponent divided by index. The remainder would be how many remain underneath for these variables with their exponents. Nice simple little trick. So if you haven't heard that before, because I know we've got some students who came from another place, love this method. Okay, let's look at some others. Okay, and I didn't mean for that answer to pop right there, but that's okay. We need to show where it came from. Square root of 16 is 4. 3 divided by 2, because the index is 2, the exponent is 3, means that 1 will come out and 1 will stay in because that's your remainder. Okay, 1 comes out, 1 comes in. 200, if we prime factor that, okay, we have a pair of 10's, so 1 10 comes out, there's a leftover 2 that stays in. K to the 7th power, exponent divided by index. 7 divided by 2 gives you 3. So 3 will pop out, but there's a remainder 1, so 1 will stay in. For our Q's, what happens? 8 divided by 2 gives you 4. So 4 come out, there's nothing remaining, so there's no Q's that remain in. So here's our information for our K's and for our Q's, so then we put it all together. I have a 10 that comes out. I have a K to the 3rd that comes out. I have a Q to the 4th that comes out. What's left over? There's a 2 left over under, and there's a K left over. And then it's fully simplified. So nice slick little process. Dividing the exponents and prime factoring. Okay, I want you to try these others. If you need to pause it, go ahead, pause and give it a shot. We have the 8 to deal with, and that comes out to be a -2 right off the bat. You need to divide exponent divided by index. Exponent divided by index. 4 divided by 3, 1 comes out, and 1 stays in. Here, exponent divided by index. 1 comes out for the y's, and 2 is your remainder, so 2 stays in. It doesn't always have to be a 1. So 1x came out, 1y came out, 1x came out, 1y came out. 1x remained under, and 2 y's remained under. This one's going to be a negative out front. 32 factors down into 1, 2, 3, 4, 5 twos. Notice that the better that you get at it, the more little tricks once you have your, you know how many factors there are. There's a group of 4, so one of the 2's will come out and one will be left behind. 9 divided by 4 is 2 with a remainder of 1. So 2 come out and 1 stays under. Make sure that you're careful where your index goes. Okay, it's a little bit harder since we're typing in our answers, but I'll show you how. Make sure though, if you are ever handwriting them, that you put your index right in the crook of that radical symbol. Okay, don't put it out. It's just not how it's written. It's not how it's typeset. It's just that since not everybody has a math editor in your work, we have to be able to enter it in your answers, and you'll have to show it in a certain way. Okay. All right. Now, sometimes you have things and you've got this and it looks like it's unsimplifiable, but if you use fractions as exponents, you can simplify, especially if you notice there's a common factor between your exponent and your index. Okay, so it almost looks simplified because you have a 5 to a power. The power is smaller than the index. Okay, looks good. But let's see what happens if you rewrite it as a fraction. Exponent over index. And wait, where did I get 2/3 from? Because 6 over 9, exponent over index reduces to 2/3. Then you rewrite it as a radical in the end, cube root of 5 squared. And you want to simplify it, making it look as nice as possible, because 5 squared can be done easily. So it's the cube root of 25 is what this looks like in simplified form. Using what you know about exponents and indexes and reducing fractions and then rewriting it in simplified form. 4th root of p squared. Exponent over index. 2/4 reduces to a half. A half is the same as a square root. So this is actually the square root of p. Okay, so just simplifying and going through like that. Okay, fractional exponents. Remember that beginning one I said that we couldn't simplify? Well, we do have a way if we think about fractional exponents. So let's look at this. This is kind of a neat little thing here, because it looks like square root 7, cube root 2, not related in any which way. But let's think about their fractional exponents. This is 7 to the 1/2 power, and this is 2 to the 1/3 power. Now, they aren't even like bases, so I can't combine them that way, but let's think for a minute, what about these fractions? Let's think about their common denominators. Okay, think about common denominators and write these exponents with common denominators. Our common denominator would be 6. Now, we don't have like bases, so we're not going to add our exponents, but here's the thing. Because now we have common denominators, this is our index. Okay, we now have the 6th root of 7 to the 3rd and the 6th root of 2 squared. Exponent index, exponent index. Now we have the same index, which means that you can put it under the same radical. And then when you simplify it out, you can take 7 times 7, 49, and get 343, and 2 squared, which is 4. Then you can multiply these things together, and your fully simplified form is the 6th root of 1,372. Okay, mind blown, right? Okay, so you probably might need to go back and rewatch that. Okay, all right. This is probably the trickiest, slickest little thing that we've done all day. All right, now since we're dealing with radicals and simplifying, we need to bounce back to geometry just shortly. We need to remind ourselves of a squared plus b squared equals c squared. Some of you have a little song going through your head right now. You could always look that up. I think I still have it tagged on the geometry site. But if not, that's fine. A squared plus b squared equals c squared. If we want the answer in radical form, that means that we're going to simplify the radical. We're not necessarily going to get our decimal form. So 4 squared plus 6 squared equals c squared. So as we go through and we evaluate that, we have c squared equals 52. But when we take the square root of 52, it does not come out even. Now, depending on the context, if it's a very practical problem, you'll want a decimal. But if it says in the directions, give the answer in radical form, which you might encounter in your math, you can do the whole factor tree method here. You want to factor 52 and look for pairs because you're square rooting. So a pair of 2's means a 2 comes out and 13 stays in. So here's the answer to a squared plus b squared equals c squared in radical form. All right, so make sure that you can give an answer in radical form in addition to just using your calculator. Notice I haven't pulled the calculator up really at all in this, so these can be done calculator free. One last thing. The distance formula. You may remember this from geometry. The variables here look suspiciously like what you would use in a slope formula, so just in case you hadn't encountered this formula in this way, the distance formula in our geometry we used quite extensively. But you can take and label your ordered pairs just like you would when you're finding slope, x1, y1, x2, y2, and then just begin to plug in your values. All right, so x2 minus x1 minus negative, be careful with your minuses, y2 minus y1. So we have 7 squared and we have 1 squared. That gives you square root of 50, which if you prime factor 50, 5, 5, 2, you have a 5 that can come out and a 2 that can stay in. And the more and more familiar you get with these, the quicker you can just do them in your head. And I'm not against doing them in your head, but if your head gets tired, then, you know, using the paper and pencil method to show your prime factoring and going back and checking, making sure that you've done a good job is great. All right, so that's all that I have for you today. Tomorrow, it's a work day on assignment 67. So you'll be working on that instead of watching a video and then turning it in by the end of the day tomorrow. So your whole 45 minutes will be spent just knocking that assignment out, getting that turned in. Friday we'll have another new lesson. So we will be looking at a quiz next week, working on getting that together. Yeah, next week I'll be giving you a quiz on sections 1 through 4, and on Monday after you turn in your assignment, because you'll be assigned an assignment that you do on Friday or over the weekend, you'll turn in your assignment Monday. You can start working on it Monday if you want. I'll have it to you over the weekend. And then on Tuesday would be your main day for working on that quiz that you're allowed to work together, you're allowed to network on. I know that some of the ones I've been saying on your honor you have to do by yourself, but this one, just to make sure that you're getting it and understanding it, I have no problem on the quiz on sections 1 to 4 with you working together on that. It's more of a learning assignment than anything. All right, but I think you're gonna do great on it, and I think you're hanging in there, so keep hanging in there. God bless you and have a great day.